So, welcome to the next lecture of the perception algorithm course series. So, we have completed our all the basic estimation theory, that is the least square, maximum likelihood and minima and maxima a posteriori, and we started very basics of Kalman filter. So, in this subsequent lecture today and the next day's lecture, we will be covering full the Kalman filter fundamentals. Okay. And this will be your foundation stone to learn the target tracking. That is very important, even sensor fusion also to some extent. Okay. So, we started with the continuous and discrete state and measurement equation, this thing. So, x dot equal to x plus bu, y equal to cx, or you can let us take a common notation, say hx. So, here you do not have any noise, x dot also does not have any noise, y also does not have any noise, and you do some continuous to discrete equivalent using some standard transformation like Tustin or bilinear transformation, some transformation, and we got it. I will tell the transformation when I tell your target dynamics. X equal to phi of xk plus 1 plus wk, z equal to h of xk plus vk. Okay. So, with this now phi is called the state transition matrix, okay, and h is the observation matrix. Now, what is the wk vk? Wk vk are 0 mean white Gaussian noise which are added into the state. So, that means now my state is, so far my state was deterministic. If you see the continuous equivalent, when I went to discrete equivalent, I assume that my process is probabilistic. So, that means there is something I do not know. So, how I would like to model the uncertainty? So, that I have to do it by putting some white Gaussian noise. So, that means I am ignorant about the real world process, I am ignorant. So, I do not know what could be some element of my x is could be unknown, or some element of my phi could be unknown, or my input control input itself could be unknown. So, to compensate my ignorance, I will put some white Gaussian noise, okay, or random excitation in an additive way. It can be done in a multiplicative way also, but your Kalman filter equations will be extremely tough. So, that is why we go in it for simple AWGN. AWGN is additive white Gaussian noise, and similarly your Vk. So, this is my to model my uncertainty, what is there into the true system. Now, if you look very closely into your first equation, your simple state equation xk equal to phi of xk minus 1 plus wk, this actually corresponds a first order Markov dynamics. So, if I go into from a basic state space equation to some kind of probabilistic approach, it is a kind of first order Markov dynamics. Why it is called what is the Markov process, by the way? Markov process says future given present is independent of past. So, that means if I know my present, I do not depend on my past to predict my future. So, if I know my state value or anything, or the process value at x t equal to time equal to k, I can easily go to the time t equal to k plus 1. I do not need k minus 1, k minus 2 or the back inputs. So, this is called first order. So, first order means I know k, I can go to k plus 1 instantaneously. So, that is this. So, that is why this state equation is kind of postulated as with a first order Markov dynamics. When I say Markov dynamics, it is a Gaussian distribution with this is your mean and this is your covariance. What is Q? Q is actually covariance of your random excitation which you have modeled in your state. So, that is your Q. What is measurement process? Measurement process is also a Gaussian. So, again, but it is nothing to do with Markov because you are propagating in the same time instant. So, zk is equal to h of xk plus vk. So, it is simply something like this. Okay. So, and now what is there are something called Q and R. These are all the tuning parameters that we need to know in when we learn the Kalman filter basics and all. Okay. What is Q? What is R? Q I told is a process noise covariance. R is called measurement error covariance. What is Q? Q means model filter mismatch. Suppose when I say this model is a mathematical model. When a mathematical stochastic model is there to represent some actual stochastic process, I do not have no knowledge of the stochastic process, how it is the behaving. So, I have to model it, and the amount of unknown is put some kind of white noise excitation. So, Q is basically called the truth filter mismatch or process filter mismatch. So, the model which I am using to approximate the actual environment, if they are very good match, then obviously my Q will be less. So, that means my model is a very perfect model. So, my Q should be less. But if it is vice versa, if my model is not a very good replication of the truth, then I have to give more Q. Okay. So, this is the very basic knowledge that we should know, because when you tune your Kalman filter, when you run your Kalman filter simulation, the knowledge of Q, how to set the Q is more important. Let me give a practical example. Suppose a car is moving, say, some kind of a straight line, and you have used, say, a straight line model to track it. So, do you think you will give higher Q or lower Q? You must give a lower Q, because actually car is moving in a straight line and you have used a linear model to track it. So, linear position velocity model. So, simple position velocity model you have used to track it. So, that is why you will lower Q. But suppose your car now is, say, moving like this in a circular contour, again it is taking, say, a turn, again it is going like this, again it is going like this, suppose it is going. Then will that be your constant velocity model will be okay? No, it is not okay. So, but you want to fit that it. So, constant velocity model may not be a good fit for this kind of a trajectory. So, you have to then give, even if you use a constant velocity model to track this kind of a trajectory, you have to give high Q value. So, that means when you say high Q values, then you say, okay, sorry, I do not have much confidence of my model. So, that is why I gave my random excitation. And when I give high Q value, that means my Kalman filter or whatever estimator you do, they will give more weightage to your measurement than your state. When it is a low Q, then it will use more importance to the state dynamics or the state than the measurement. So, this is the funda. So, with this fundamental, you can do this kind of a Q and R kind of a tuning. Now, I will tell, when I learn the Kalman filter, I will tell how to estimate, how to give the Q value and how to give the R value. R is normally a very straightforward. R is actually your measurement reports, whichever you are coming. You take the measurements and then you fit it to a kind of a least square or any kind of autoregressive moving average, some kind of curve you fit. You get the error, what is your R minus measurement error of your actual measurement data minus the predicted model data. You check whether it is white or not, and then you empirically calculate your standard deviation. Okay. So, this is actually some R you can directly find out from the observation data or from the sensor report. Okay. Now, I will go through the concept of estimation first. Most of them who are from the control system background in PG, they must have courses in their estimation theory course. So, prediction, filtering and smoothing. So, what is prediction? Prediction means you use measurement till zk minus 1 and you predict the state at time t equal to k. So, this is called your prediction. So, you are using one step back measurement to predict the next time step. So, this is your prediction. What is filtering? You include zk. So, which state you are estimating, that time stamp, you include one more measurement here. Okay. So, that is your filtering. What is smoothing? Smoothing means you do some kind of back propagation. So, you use future measurement to predict your current state. So, that is called smoothing. So, at t equal to k, you use k plus n minus 1. So, you use a future measurement to backtrack it and use it to estimate your state. So, this is called smoothing. Okay. Now, I will say the estimation objective. So, this is my state space and say this is my observation space. So, just in from some kind of mathematically I would like it to show. So, this is your say state. What is the state? State is the underlying hypothesis. You do not know. I only represent state with some measurement. So, that measurement say is given x. That was at k minus 1 and here also xk I have a measurement here and I have this first order Markovian dynamics of the system that I know. I use that model with a process noise is this, process noise have this statistics. So, this is your system model. If I go write in a probabilistic way, this is called Markovian transition density, or simply your if I write it here, you can see it, actually it will be f of x k minus 1 into q, it is a Gaussian distribution q. Measurement likelihood is this likelihood function, simple. So, you can write it actually h of x k comma v k, okay, or even probabilistic format you can write of z k given x k, instead of p I wrote g, so same thing only. What is the objective? Probability of x k given measurements up to time t equal to k, that is what filtering says. So, it is simple, kind of similar to map I am doing. Okay. So, you have the measurements up to this, you want to predict the system state at x equal to k, that is the filtering. Now, I will just highlight Bayesian estimation theory briefed, and then we will go to the Kalman filter. Kalman filter is exactly same the Bayesian estimation theory. So, suppose you have two cycle, one is called prediction cycle, another one is called estimation cycle. What is called prediction cycle? Obviously, you have a predicted state distribution at t equal to k minus 1. So, this is your predicted distribution. When I say probability of x k minus 1, this k minus 1, this means what? This means you have estimated your state up to using z k minus 1, and you will get a state x k minus 1. You have used this much measurement, say x 1 to k minus 1 z you have used, and you have estimated this. Okay. So, this is called this is your estimated distribution. So, now you go through a prediction. How will you do prediction? Through your Markovian model or your state model simply. Forget the word Markov. You will use the simple state model. So, with this you go to your predicted distribution. So, that means now you are from k minus 1 you go to k. So, your measure up to, but your measurements is this much. So, you go k, okay, and then your measurement at that times instant has come injected here, and then you estimate your estimated distribution. So, a probability of x at time t equal to k given z 1 to k. Okay. So, this is your prediction cycle and this is your estimation, prediction cycle and estimation cycle. So, from estimation at k minus 1 distribution, you use your state dynamics to calculate your predicted distribution, and when you have got your predicted distribution, you insert your measurement at the predicted distribution and get your estimated distribution at time t equal to k. Now, I told everything and you start the recursion. This is a recursive process, you start the recursion with the initial state distribution. Now, I told at very beginning in my lecture that all assume to be Gaussian. Why Gaussian? Gaussian means, again I am repeating, two statistics. First order statistics, that is mean, second order statistics, that is variance, that is sufficient to represent any distribution, and that thing we will be covering. So, in a Kalman filter, you must have, if you have seen in your estimation theory or some other course, Kalman filter always have two things, x and p, x and p, x and p. X means state, p means error variance. So, when your estimated state distribution is there x k minus 1, k minus 1, z 1 to k minus 1, when I am representing it, I will have some kind of x hat k minus 1 k minus 1 into p of k minus 1 k minus 1. Okay. I have that. So, I have mean, this is my mean, this is my variance to approximate this distribution. With my dynamic model, with my state transition matrix, whatever you say, I got this predicted value. So, I got a predicted value. So, x hat k minus 1 p of k minus 1 through my state transition matrix. Once I integrate my measurement, I got x at kk error variance kk, right. We got all the things. So, this is what your Kalman filter about. So, this cycle is called, from here to here, this cycle is called pred cycle, prediction cycle. This to this is called EST cycle, and the cycle repeats, provided you feed the cycle with a initial state x0, p0, initial state and initial estimation. This is all about Kalman filter, nothing else. Okay, I will come back this slide later. First, I would like to tell you the, okay, maybe I can complete it. So, what I told, I have the same thing actually I have written it here. So, you have, this is your prediction block, this is your prediction, sorry, this is your estimated state at t equal to k minus 1, you have x k minus 1 given z 1 to k minus 1. So, this is your estimated distribution at k minus 1 using the state transition matrix f, say, or phi, whatever you say, assume. You predict it to k minus 1 at t timestamp t equal to k. So, this is your predicted distribution and you insert your measurement here, you got your estimated distribution. So, this is the recursive cycle and the cycle repeat, that is what I just told. Now, there is something called Chapman-Kolmogorov equation. So, when you do in a Bayes theory, or if you want to do, say you are playing with only distribution, actually Kalman filter plays like this and you got in some algebraic equation which are kind of output of this time update and measurement update. So, you have your predicted distribution is equal to integration of your Markovian dynamics, probability of xk given xk minus 1 is actually your phi, your Markovian dynamics, and this gentleman xk minus 1 is actually estimated distribution at k minus 1. So, you are given this value, that means when you say estimated distribution you are given one mean one variance. Distribution means you always remember one mean one variance you have given. With the state transition matrix you integrate it and you give it, you generate another predicted distribution. Now, your predicted distribution is there, you apply Bayes rule, simple Bayes rule, your Bayes rule. So, you have to calculate this. So, this is your likelihood function, this is your actually predicted distribution and this is say is your constant. This is you remember this thing. So, this is the normalization constant. You calculate your estimated distribution. So, that means when I say probability of z given xk, I am incorporating a z here, measurement here. Okay. So, you can see this. So, this is your Kalman filter, this Bayes filter, particle filter I won't talk about right now because it is a different thing, but particle filter actually if you understand the Bayes filter, then you will be able to understand the concept of particle filter, nothing difficult. So, here is your estimated distribution, again I am repeating estimated distribution at k minus 1. How I am kind of doing it is approximating it with a mean value at estimated value at k minus 1 and a variance value at k minus 1. Then I use my state transition matrix or phi matrix to go some prediction by some equation say. With that equation I get another mean and another covariance matrix at time t equal to k. I got it. Then here my measurement at that time instant, that k time instant has inserted here and I got another estimated distribution with another mean and another covariance. So, this is the Bayes filter and Kalman filter. If you read it properly, they are kind of same. Okay. Particle filter you just ignore, particle filter is different context, I won't go through here this thing. So, this is called a single target Bayes single target filter. Now, I just jump to the, since this is not an estimation theory course and I have to start talk primarily the perception functions, estimation theory is kind of taught as a basics or to basic building blocks, so that you can write your own perception algorithms and all. So, you have two cycle as I mentioned, your prediction cycle, your estimation cycle, your prediction cycle, your prediction state and prediction state error variance you got like this. So, your prediction states are predicted states are going here, then your estimated states actually starts. So, first you calculate your what is one, the measurement is inserted here, you calculate what is the measured value minus predicted value, that will give you the innovation. You calculate the innovation error variance, once you get the innovation covariance, what is the output error covariance, then you compute something called Kalman gain, that is the correction factor. So, your prediction plus your correction Kalman gain into residual will give you the estimated state and estimated state error variance, and it is preparing for the next cycle, the cycle repeats. So, this is all about the Kalman filter. I hope this is understood. Okay. Just I wanted to give you an example for the a simple information exchange in a 2D tracking in one Kalman filter cycle. What I told. So, just I have drawn everything, the same thing I am trying to repeat again using a kind of pictorially. So, say you have a I would say estimated state at k minus 1, and say that is why I have written it here, okay. And you have your error variance is here. So, this circle, the radius of this circle say is your error variance. So, you got it p k minus 1 k minus 1, okay. So, this is your state, same this center point say is your state, and this fellow, this gentleman is your p k minus 1 k minus 1. This is a 2-dimensional tracking example. So, you have seen in the ordinate or the y axis I have put a velocity, and my x axis I put say position, okay. So, position and velocity, okay. When you put a position velocity of a 2-dimensional tracking, it is actually the trajectory will be actually a circle. So, that is why some circular arc is kind of shown, and the radius is actually your error variance, okay. So, whenever the circle is large, that means error variance is too high, whenever circle is small, the error variance is small. So, you are in a prediction, you are at a time t equal to k minus 1. So, k minus 1, you have your state estimate as x at k minus 1 plus you have your x dot k minus 1 is here. So, say this is your center point, x value is your position, y value is your say velocity at t equal to k minus 1, and the circular and if you see the radius, because radius you can see the radius actually it is actually say p k minus 1 k minus 1. So, that is your error variance. Now, you are running a Kalman filter. From this small big circle you go first prediction. So, that is this big circle. When you do the prediction using your state dynamics, so that times no measurement at z t equal to k has come, it is only using your phi state transition matrix. You go such a large circle, big circle you got. So, big circle when you got it, here you see this is actually your x k and sorry, not this one, this is actually x k plus minus 1, and this is actually your x k, okay. Okay. Just this was, I am sorry it was not written here. So, it is x k minus 1, this is x k. So, here first you go here. So, here you got your predicted values. So, your predicted value is this x k minus 1 is your position, x dot k minus 1 is your velocity. So, at this center of this big circle, this is your say your predicted value, and what is the error variance is actually this, say the radius you can say. Now, you incorporate z here, say z is something here. When the z is something here, then actually you find, and z is incorporated to this. When you do your estimation, you see another small circle has come. So, your actual estimated state is lying here, and your estimated velocity is lying here. So, this is the your actually I would say central point of this smaller circle. Now, you see the thing, this is the largest cycle, okay. This is the predicted cycle. From here you have predicted it, so you have your error has gone up, okay. Your error has gone up, such a big circle you see, and then when you are incorporating measurements, your error is again coming down, shrinking, and this one is slightly less than this. You see the circle radius here and circle radius here. So, that means as your cycle is propagating, your this thing, your circle radius is reducing, that means your error is reducing. So, that means your error is kind of a reducing, okay. So, that is the purpose of filtering. So, as you propagating, your error variance is kind of a reducing, and you see your xk, your zk is say in the left half of your predicted state. So, when it is in the left half, when your predicted is here, xk will be somewhat within this, between zk and xk, okay. So, you can see here, so it will be within this, and obviously your pkk minus 1, you can see the length of this two circle, this is larger circle, this is smaller circle. So, your estimated this k will be little even lesser. So, once we do the error covariance plot, you can see now how your estimation covariance will behave. So, it is say at your actually initial guess you have started, okay, and then you have jumped to predicted P10, the first cycle. Then again your measurement has come. So, you see now suddenly it is coming down, again it is going up, it is coming down. So, these are all estimated distribution. If I now do a smooth curve fitting, you see it is curve is coming like this. So, this is your actually P of k k, okay, P of k k, and this is your actually predicted value. So, predicted is like this, this is a predicted curve P of k k minus 1 P k k. So, you see your as the time progresses, your error covariance is kind of reducing and suddenly it goes to a constant. Okay. So, that means there is a certain bound, beyond that your error variance won't go further. When we will, there is some other way to postulate it, that we will be talking in subsequent classes, but for the time being that is the purpose of your Kalman filter. So, Kalman filter is starting from an initial large error and gradually as it is kind of coming down, then actually your state started following your truth if you are doing in a simulation. Okay. So, it is started following your truth. So, this is the fundamental of concept of a Kalman filter. So, the state error, now if I plot the state error, so state error now actually this is Kalman filter x minus x at whatever Kalman filter equations are giving. Now, if I plot my state error, estimation error will be something like this, and this gentleman will fall into something called plus minus 3 sigma bound. What is the plus minus 3 sigma bound? This is actually your root p, say standard deviation if I say, and this is minus of root p. Okay. This is the time. If my estimation error is lying within these two bound, that means, so this is your plus 3 sigma, this is your minus 3 sigma. If it is lying within this bound, then there is a thing that with a single run Kalman filter I can confirm my estimation is converging. Okay, this is not diverging. So, that means when I plot my true versus estimate, it is kind of holding like this, it is holding like this, it is not going like this. So, it is holding like this. Okay. So, that means my Kalman filter is converging. Okay. So, this is actually the one fundamental principle of a Kalman filter. This I will next I will tell you in this lecture, I will tell few more things. Normally, when we run the Kalman filter, there are two modes. One is called single run Kalman filter. For a linear Kalman filter, okay, Kalman filter first assumptions, then if I go summarize, the system should be linear. What is linear system? Linear system means your principle superposition, principle of superposition and principle of homogeneity, both are kind of will be applicable for a linear system, good linear. State distribution is Gaussian, measurement noise, process noise is Gaussian, and last thing is very important, is called my state. Kalman filter always assumed unbiased estimation. So, if there is a bias in your measurement, your Kalman filter will fail to estimate and the estimation error will be on top of a bias. Suppose you get a sensor and that sensor is having some bias on it, and that bias will be reflecting when you plot the estimation error. You can yourself see. So, when you say unbiased estimate, that means expectation of x, this say my estimation error, prediction estimation is 0, expectation, then it will be coming at xk is equal to 0. Okay. So, this is actually your predicted error, predicted thing, there is no bias, this is the estimated thing, estimated state. So, Kalman filter is a unbiased estimator. This is a very important concept. If you see, if instead of 0, if you see it 0, C or some kind of constant value, that means your measurement is biased and your Kalman filter won't work. Your estimate, if this is your truth, and you will get an estimate like this or estimate like this. So, some constant bias will be there. Okay. So, your estimate has to be bias free. Okay. So, with this actually now I would like to close this session. In the next session what we will do, we will take some more properties of Kalman filter, and they are very important properties when you will simulate the Kalman filter, that is important, and we will take one example of a vehicle collision avoidance system in next class that we will be discussing. Okay. Thank you. Thanks for your time.